So now that we had a chance to talk about the various parallelism frameworks in Java, it's time to start talking about the parallel streams framework, which will be the first of the 3 frameworks we're going to cover. And I want to begin by describing what the aggregate operations are in Java's sequential streams, which we talked about before, in the context of our SearchStreamGang program. And we'll see how that can be applied in the parallel streams framework. And we'll give a high-level view first time, and then we'll kind of drill down to this from lots of different points of view. So hopefully this is just a quick recap. A stream is a pipeline of aggregate operations that process and typically transform some kind of sequences of data, elements, values, whatever you want to call those kinds of things, much like we talked about before with our SearchStreamGang program. These aggregate operations apply these pipelines of behaviors to elements that flow through the stream. As you can see here, we have intermediate operations. We have operations that are terminal operations. And by default, if you just say stream, as we do here, everything runs in a single thread of control. So no big surprise. There's one thread. It runs all the processing. When you say parallel stream instead of stream, then the input gets partitioned up into substream chunks that run in something called the common fork join pool. We'll talk more about what the common fork join pool is shortly, and we'll cover it in great detail a little bit later. And as you can see here, the data flows through here, and it gets run in different chunks. The threads that run in this fork join pool, which is, of course, managed internally, so you never have to see them yourself. You don't really actually have that much control over them in some sense. They will non-deterministically process these chunks. And we'll talk shortly about what non-determinism means in this context and why it's relevant and why it's important and the benefits it provides and some of the challenges it provides to developers of the parallel streams environment. And then, of course, a terminal operation will take all the results that come from those various independently processed substream chunks and merge them all back together again into a single result using some kind of reduction operation like collect or reduce or whatever. One of the key things to do, always keep in mind whenever you program this kind of an abstraction, is to use stateless lambda expressions, stateless method references in order to do the behaviors. And if you follow that simple advice, then life is much easier because worrying about synchronization and race conditions is a hazard, as we'll see shortly. So if you follow those rules, if you keep your behaviors stateless, then you typically can make very minuscule changes, going from stream to parallel stream or vice versa, to switch from a sequential stream to a parallel stream. Now, sometimes there's more to it than that, but that's the first cut. And you'll see, speaking of small differences or changes in behavior, if you take a look at assignment 2C, which I released yesterday, if you watch the video and look at the skeletons and run the tests and so on, you'll see that it's a little different from assignment 2B. It's not quite as minuscule. The changes are not quite as minuscule, but it all follows along the same basic ideas of going from sequential streams to parallel streams. So please take a look at that. Now, one of the key points to make in all this, and the reason why it's taken us, a number of weeks to get to parallel streams, is because pretty much everything you've learned for sequential streams applies directly. So if you take a look, there's lots of operations that are defined in the Java Stream interface, and by and large, most of them apply just as well to parallel streams as sequential streams. Not all of them. In particular, some of them don't work as well for parallel streams as they do for sequential streams, but they'll work. They'll give you the same behavior, just some of them don't scale up as nicely as others. And we'll talk a bit more about that as we get further along, too. Just to make things concrete, and we'll look at this in more detail shortly, the search with sequential streams example that we've been looking at up to this point looks pretty much identical to the search with parallel streams example we're about to look at, and the only difference is it's parallel stream versus sequential stream. So that's cool. You can make these improvements without having to do a whole lot of work, as long as you get it right with the sequential version. And let's face it, it's a lot easier to debug and program sequential streams than parallel streams because things kind of go in a more orderly fashion. Literally, they go in a more orderly fashion. So you can basically think of parallel streams, you can think of parallelism in general as an optimization. So it's kind of like, giving the -o flag to a compiler. You're telling the compiler to take its existing strategy and then improve the code that's generated while keeping it semantically correct. And in some sense, you can think of parallel streams in somewhat of the same idea. So it just is a more advanced way of taking advantage of multiple cores without requiring a lot of extra work on your part, which is good. And of course, you got to be careful how you program things so that you don't end up with race conditions. And race conditions can occur if you have state that's being accessed from multiple threads in the parallel stream that isn't properly protected by some kind of synchronization. So shared mutable state is the root of all evil, as you can see if you read this link down here, which is somewhat humorous, but it's true. And we'll talk more about shared state and how that applies shortly and how to avoid dealing with issues of shared state. Okay, so that's just a quick overview of the transition from what we talked about before into the next topic, which is parallel streams.